Okay, so we are getting closer to the end. We'll have at least two more podcasts, as I said. And let's run through the paleo aspects and then we'll look at some future projections as well. Uh, Oops, here, my computer is becoming quite, yeah, anyway. So as I mentioned, the review paper looks carefully at all the previous studies on paleoclimate, and the idea is not that the data is good enough to track western disturbances, but you can look at winter precipitation and try to extract some information about western disturbances, because you know that western disturbances have a large contribution to the winter precipitation in the region of interest. So this is just a kind of a prop actually. So Greenland dust, so these are reconstructions, and we'll look at the mid-Holocene, and these are various things, how they are derived. Greenland dust is used to extract some information on the strength of the Siberian anticyclone, North Atlantic oscillation, we know that what that is, and flood information can be derived as well using this approach, where grain size, negative NAO indicative of floods in the southern Alps, so correlations are used to indicate that. Hurricanes are derived from grains in the sediments and so on. Interhemispheric temperature anomaly and intertropical convergence zone, ITCZ, which is an indicator of various climate variability proxies, and winter monsoon, which is what we are most interested in, and you can see a clear signal there. This is looking at, let's see, winter monsoon, this is G. So winter monsoon, ancient DNA-based reconstruction for northeastern Arabian Sea. And then there are speleothems here, and western disturbance, westerlies and western dispense. It's late in the day. Westerlies and western disturbances using delta O18, so that's H here. Speleothems delta O18 based precipitation reconstruction for the northern Levant, which is the Middle Eastern region, and stacked lake isotope records as proxy precipitation evaporation regimes over the Middle East and Iran. And the present days, so we are basically going from about 7,000 years back towards the present, and this is the early neoglacial anomalies interval that is shaded here. Okay, what does this all mean? Just look at the summary of paleoclimate study results that indicate the estimated strength of winter precipitation and hence WD frequency over the Western Himalaya, and the level of consensus among recent studies for selected geological periods. Somehow this room is making me late Pleistocene, 60 to 18 kilo years ago. So until the end of the last glacial maximum, 18 to 12 kilo years ago, until the end of the Younger Dryas. I have discussed this elsewhere. You can look up what they mean. Winter precipitation was strong and quite strong and variable, so consensus is good from few studies but poor on the second one. Early Holocene, 12 to 18 kilo years ago, Greenlandian evidence, winter precipitation was very weak, but the consensus is good on that. Mid-Holocene, not Grippian, so 8 to 4 kilo years ago, the 4.2 kilo year event as well is included in here. This evidence, winter precipitation was weak, and during the 4.2 kilo year event, it was very weak. So agreement is very good, and there are many historical evidences associated with these in terms of perturbations on the civilizations at the time as well. Late Holocene, the Meghallian period has many sub-periods within that with winter precipitation being weak, strong, weak, weak, and strong. So the Roman warm period, medieval warm period, and the Little Ice Age are included here as well. And the consensus is very good, 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 but the studies are few in number and very good. It's a disagreement on the region, though, even though the results agree. So when you have evidences from various regions, calibrating all of them together is always tricky. Sometimes you see the signal seems very strong, but sometimes they are mild. Time resolution is very weak, and then you are taking very local data like Greenland and then trying to extrapolate it to winter precipitation over the study region and so on and so forth. So I won't say much more on that. The other thing that gets discussed a lot is the trends of WD activity, and there are many studies, as you can see, and the conclusion is that basically there is no robust evidence at all that there is any detectable trend in the WD frequencies, even though people keep writing about it and several claims are made. Okay, this is looking at all WDs and strong WDs. So this is trends in WD frequency from 1952 to 50 to 2022. The number of unique tracks passing through each of the 2.5 degree each 2.5 degree by 2.5 degree grid box per month is counted, aggregated by season, and the trend is computed. Two seasons are shown. A and B are where is the labeling? So A and B are December to March, and C and D are April to June. To determine whether trends are sensitive to WD detection thresholds, trends for strong WDs, i.e. those who speak 350 hectopascal relativity is in the top half of the population, are given in panels B and D, so separating the strong ones. Stippling indicates where trends have statistical significance, and the gray boxes indicate the region typically used for aggregating WD statistics. So you can see here track density trend, WDs per grid box per month per century. So statistically significant in these boxes, but the conclusion is that they are really not, this is the let's say spring summer season, and this is the winter peak season, and there is some indication that maybe trends are there throughout the year, but here strong WD is only so in the winter, but you can take it for what it is. The conclusion of the paper is that the trend signature is not robust, which is consistent with these results here. You can just look at the figures. They are looking at frequencies, frequency anomalies, percentage anomalies, and GPH variability, wave power. Various proxies or regime days, various proxies are used to estimate WD trends, but results are not very convincing. Trends in winter DJFM precipitation in millimeters per month per year over Pakistan and northern India since 1980, as recorded in 4 data sets, 2 gridded gauge-based data products and 2 reanalysis products. Stippling indicates where trends are significantly different from zero. Again, you can see that IMD says it's significant here, but Aphrodite, slightly different period, but it puts it way over there, and little bullet here. This is a trend in December to March precipitation trends. So ERA 5 is very different. So what do you make of it when you have different products producing, IMDAA is another reanalysis as well. Different products producing very different looking precipitation trends. Precipitation is very difficult for models. Temperature trends are done fairly well, and the decorrelation scales of temperature are larger. Precipitation can be very local, especially in complex mountain terrains. Then what do you do with these? Well, just take take them for what they are. We'll read all the future questions where all these questions will come back again, or these issues will come back again. This is the rate of glacier surface elevation change as shown in ice flow velocity for the period 2000 to 2016. Sorry, the surface elevation changes shown together with changes in ice flow velocity. The size of the circles is proportional to glacier area. Okay, the red box marks Karakoram and the surrounding area, which is this huge box here. So surface elevation change in meters per year and glaciarized area is in kilometers squared, going from 200 to 3000. And you can see the almost all of them are down arrows except for a few where you have there is the Karakoram anomaly that we mentioned. It's complex. The data is not as dense and long as you would like. It's only from 2000 to 2016. So obviously you have to be always careful about decadal variability versus trends, and even the decadal variability can be modulated by global warming and so on and so forth. The ice flow velocities change in percentage per decade is shown going from -30 to +20. So decreasing versus increasing. So you can see those are also positive in some areas. So very complicated figure, but here you can see how signs are all mixed up. There are some negative decreasing ice flow velocities and some surface elevation change being positive and increasing flow velocities as ice flow velocities as well. What can you do with these? Well, go back and read more if you want, but I find these kind of things to be it's very hard work. People do a very diligent job of taking data and trying to infer trends and so on, but glacier business is even more complicated than precipitation business, because you have to use the technique that measures elevation changes. People go and put a bamboo stick and measure year after year, but this kind of data is going to have discontinuities and so on, because bad weather can make it difficult and so on and so forth. So here we are looking at projected future trends of WD activity under historical and RCP 2.6, RCP 4.5 and RCP 6, as well as RCP 8.5 emission scenarios. I have discussed the details of these scenarios elsewhere. They are representative concentration pathways with the numbers 2.4, 4.5 representing the radiative imbalance at the end of the century in 2100. 2.6 watts per meter squared, 4.5 watts per meter squared. RCP 8.5 is considered the business as usual scenario, where we basically keep burning fossil fuels and don't do much, and we'll get the maximum warming. But you can see the trend here in terms of WD frequency per proxy anomaly or proxy anomaly percentage is, the range is quite large, but all of them show a declining trend in WD frequency, except this one here, the dotted line. Color shaded regions indicate the interquartile ranges for the historical and RCP 4.5 track frequency. So the idea here is that you have some idea of the, so these are different papers. Hunt et al. Is all over the place here. Krishnal et al. 2018, 35 kilometer global GCM estimate in this dotted line, and Hunt et al. In CMIP 5 multimodal ensemble, I think multimodal mean. Okay, so what do you do with this? Again, I've always talked about how the uncertainties in the first couple of decades is totally related to internal variability, model uncertainties, etc. After that, the scenario uncertainties begin to dominate, and you can see that the differences are not large in the first 10 to 20 years, and then they begin to diverge. So you have to wonder about what to do with this kind of information, where different scenarios produce different results. Of course, scenarios are supposed to capture all potential outcomes of geopolitics and choices that humanity makes for energy, population growth, mitigation, and so on and so forth. Okay, so I won't say more about this. This is a bit more on spatial maps for various scenarios called shared socioeconomic pathways, which are next version of RCP. And these are projected change in winter precipitation, DJFM, A to C, that's precipitation, and snowfall in D to F from the current climate, so 1960 to 2000 baseline, to the end of the century, 2060 to 2100, where the scenario uncertainties will be dominating, and these are obviously for different shared socioeconomic pathways, SSP1 2.6, SSP2 4.5. So they are combinations of RCP and choices society make for minimizing conflicts, regional conflicts, and how they grow, whether they will use fossil fuel unabatedly. So there is an axis of mitigation challenge being low or high, adaptation challenge being low or high, and there are certain sustainable pathways. So SSP 1 2.6 is the most benign one in terms of trying to stay below 2 degrees C by 2100, for example, and this is the business as usual. Again, here you can see snowfall change, all negative mostly, and some positive numbers, and the precipitation change is mostly positive and largely negative over here on the southern edge. What does this mean? Obviously, you have to be careful, because if winter precipitation is going from snow to rainfall, then it can be a problem, because then glaciers will still melt even though rainfall is increasing and not snowfall, and so on and so forth. So such details, are they reliable? I'm not so sure. I think the uncertainties are too large. From Jury et al., this is median climate change of precipitation December to April under RCP 4.5 and RCP 8.5, and you can see the differences here. Right? So similar regions, but very different results. The map is zooming in differently. Here is Nepal, north central to Pakistan and India, and so on and so forth. So median climate change of precipitation for RCP 4.5 and 8.5 scenarios at the end of 21st century. So it's comparing 2071 to 2100 with 1981 to 2100. The respective levels of agreement between the models, right column, unreliable for less than equal to 50% of models show significant changes but agree with anyway, it's a complicated way of saying that the models are all over the place, but we try our best to extract signals. So here, unreliable, not significant change in light green, and significant only in these dark green places. So what do you do with this? Wow. I'm just showing because it's part of the review. Adapted from figure 11 of Hunt et al., where 40 historical WDs were simulated in WRF, which is the Weather Research Forecast Model, a regional model, at a resolution of 20 kilometer, which is relatively high compared to the global models we have looked at. The left panel shows their composite vertically integrated moisture flux. So this is the control run, addition from Q prime and U prime, so humidity change and wind changes. So this is the next two panels show the change in composite vertically integrated moisture flux from changes to tropospheric moisture content and dynamics, so circulation change, when same WDs are simulated in the RCP 8.5. Basically, they are taking historic WDs and trying to provide circulation change and moisture change from future scenarios to see how things will change. Is this useful? Basically, you are downscaling. You're taking global models. WRF is a regional model, so you will be giving boundary conditions and trying to see what the WDs will do. Basically, looking in summary is the best summary of the key statements that have emerged from WD literature in the last decade, along with the confidence in those statements. It kind of summarizes how much remains unknown, even though when you read the review there is lots of papers, publications, makes you feel like you know so much, and yet they are all bits and pieces that don't tell you the complete story, because we don't know the complete story. Okay, So I won't read all of them, but you can see here confidence goes from high, medium, very high to very low in one case. Tracking algorithms are a useful tool. WD cyclogenesis mostly occurs over ocean or downstream from mountain ranges. WDs intensify through baroclinic instability, sometimes with moist or orographic coupling. WDs primarily affect the western Himalaya and surrounding mountain ranges. WDs have mid to upper tropospheric vorticity maxima with ascent ahead of their center. So since most of them are high or very high, I'm not going to read the confidences, but here medium WDs reduce pollution levels through increased rainfall and near surface winds. The confidence there is medium. The very low one, WDs can trigger avalanches in the western Himalaya. Confidence there is very low. Interaction, let's see some very high ones. WDs intensify through baroclinic instability, very high. WDs primarily affect western Himalaya. WDs have mid to upper tropospheric vorticity maxima, very high. By recharging glaciers and the snowpack, WDs are vital, very high. WDs provide conditions conducive to widespread fog, very high. So you can extract out of these what are important things to predict, where the process understanding has to be extracted. So if confidence is high, can we translate that to somehow improving overall understanding and especially predictions? Models are not doing so well, as we saw. WDs are the primary cause of pre-monsoon lightning over North India. Confidence seems to be high. Lightning kills a lot of people in India, but not necessarily just over North India. Nonetheless, wherever you can get links to predictable events to lightning. Lightning is hard to predict, but if you can predict likelihood of lightning associated with WDs, you may be still able to save lives and so on and so forth. Okay, lots more. I won't read all of them, but very low one here. Climate change will cause WD frequencies to decline. We saw the trend plot, but the confidence is very low. And other thing, a positive phase of IOD leads to increased WD frequency, very low confidence. And climate change will cause the ratio of snowfall to rainfall to decrease, very high. So with the warming, precipitation may increase, as I said, but it could be coming at the cost of snowfall. So that may be having other challenges that will have to deal with. Okay, so this is a fairly long section with over total of 33 questions that they pose as future research questions and challenges. That's a lot of questions, right? But at least they're being honest. As I said, it's an incredibly long review, so I will read it, and we'll use that podcast, the last podcast, as the main summary of the review paper, because I've been very brief with the rest of them, even though they are taking time. You can imagine just how long it is, right? But the future questions will tell us what we already know and what we need to know. And who is it important for? Obviously, India worries about it a lot, and Kieran Hunt has gotten hooked to it, even though he's in the UK. They work a lot on the monsoons. It's a good dynamical question, so it's good that he has gotten fascinated by the WDs and working so much on it. We'll hopefully see that maybe he will improve the predictions somehow in the end as well. Okay, so we'll come and try to wrap it up in the next podcast. Maybe I'm tired today and I'll do it tomorrow. Okay, anyway, see you in the next and last podcast.